So good afternoon, everyone. Now we are at the last session of this first day of the in-house symposium. And the last one is the most awaited session. So let me once again welcome our director, Professor Annapurni Subramanian, to deliver the welcome address. Good evening. I welcome you all to this session. This is the Foundation Day lecture Shobha Chaudhary, Director IIA, this evening. I just want to give you a 2 minutes introduction to what this program is about. So IIA founded on 1st of April 1971. We have not had the Foundation Day lecture so far. We are introducing it this year. The reason being, we do the Founders Day lecture, which is attributed to our founder. You can see the bust of Professor Vailabapu there, and he's a founder, and we celebrate the Founders Day. But when we were celebrating the Golden Jubilee year, we had the year-round celebrations, which culminated on the penultimate day. So last year, 31st of March evening, we had a special lecture by Dr. Kasuri Ranga on NEPT 2020. So it became very evident that it is important to commemorate that and continue with that. So continuing with that practice, we are having the Foundation Day lecture today, and we also included the in-house meeting so that we can talk, listen to each other's research and what's going on, etc. So we started this program this morning, which we are calling as the Foundation Day Symposium. So started in the morning, we were going to several lectures, and now we are reached the Foundation lecture time. So it's very, I'm with my pleasure to welcome the speaker, Shobha Chaudhary, to IIA to give this Foundation Day lecture. We also have a special guest this evening, Professor Avinash Chandra Pandey, who is the chair of our Governing Council, and we are very happy and thankful for him to be here on this occasion. Thank you so much. I also take this opportunity to announce the Jai Avasar Awards. We just completed the evaluation of the entries for the joint Aries IIA Avasar program, which is for writing, augmented writing skills for PhD students and PDFs. This is a joint Aries IIA program. We have set up a committee for evaluation and they have given the results. And last year also, we had announced the results on the same day, and the certificates were given by Dr. Kasuri Ranga. So continuing with the same tradition we decided, I would like to announce the results. I also wanted to say that many of our students are still traveling back from the Astronomical Society of India meeting. So many may not be here, but I'll announce the results. But whoever is available, please, I request Shomak to hand over the certificate. Yeah. So among the PhD students, the first prize for PhD students go to Deepak of IIA. It's not here. Okay. And second prize goes to Shadabda Majumdar of IIA. Third prize goes to Manika Singla among the PhD students. I think like guys may be there, but not. And we have a certificate of appreciation for Shilpa Sarkar. She's from Aries, Narita. So congratulations to all the women. And there's also a cash award with that will also be transferred. And one of the postdoctoral fellows, the first prize goes to Sushmita Rani and so she is there. So congratulations. And the second prize goes to Abhijit Bandyopadhyay from Aries. And third prize goes to Varun. So we will send across the certificate as well as the prize to. Thank you, Professor Subramanian. May I now request Professor Avinash Chandra Pandey, Chair, Governing Council, IIA, to address the audience.
I congratulate Director, Distinguished Trade Relations, scientists, engineers, members of academic staff, scientific staff, technical staff, my dear students. This is an occasion on which we have to remember the founders, the vision they had, and how difficult it was for them to envision something and then get it implemented. So the responsibility on us is to implement and to take it. So today we remember all the founders on this day, and this will be our tribute. Take it as a challenge because we have passed through a very unprecedented time, such COVID, but we have learned a lot within this period. Now you can connect with this hybrid mode. There are many people not sitting here also, but from other places. So following COVID appropriate behavior, we have to recover the losses which were, if any, there while completing the projects, our whatever targets we had in coming days. So these are the things which we need to emphasize, especially on this day, how we are going to move. Thank you very much.
So may I now welcome both of you, Professor Pandey and Professor Rai Chaudhary, to water these two saplings, which will be later planted in our IIA garden. So may I now request our Dean, Professor Ishwar Reddy, to introduce the speaker.
So it gives us great pleasure to have Someone Chaudhary here. They do talk, they do foundation. I sent a message to Soma to be able to see the things like that. And then if you don't have them, I mean, source from Google. So I have done something there. So may not be knowing for to have that. So Soma started his journey and Sage Avian College. Took place second time to entire West Bengal. Later on, he moved to Presidency College, BSc 6. That he moved to Trinity College, Oxford University. There he did BA in physics, MBA as well. Then he moved to the University of Cambridge to do his PhD with one of the pioneers in galaxy evolutions and things like that. So after his PhD, he spent a couple of years at the University of Cambridge and then Harvard, and later on he moved to UConn. So for 5 years, multi-variable studies of galaxies and their evolution. So after 12 years spending in Birmingham, this is not Presidency College, University. So in 3 years, he goes to physics there and then Dean of Sciences there. Then later on, he was asked to take the responsibility of a UConn. So the 3 onwards, he has been there as a director, providing a lot of guidance. Apart from all of these things, he's a great science communicator, and then he takes extraordinary interest in educating people and then inspire people. And then he's one of the first ones to initiate this interpretation. I think he led 2 groups, 1999 and 2000, and that was the first time. Some of them got gold medals and then. So I invite Soma Chaudhary to deliver the Einstein's craziest legacy. That's what we recently heard.
Thank you very much. You can hear me. This is a new experience. Lecture in person in 2 years. It's really good. My lecturing skill. Thank you for this amazing lecture. It tells you all kinds of things you have to trust. Thanks. I know that this is an audience of astronomers, that there are a lot of people out there also listening or will listen on the recorded version. So this is not going to be a technical talk. I will have, however, some things for astronomers. It's going to be more of a public talk for people who don't specialize in astronomy. And so I wanted to talk about science legacy, and you're talking about scientists who and what impact a scientist has on science. And a good time to inspect their legacies 3 years later. A lot of people look back and say, we still work with Einstein? We still, we're doing the same thing. Like that. And so how long will his legacy last? And the title of this talk is not original. I took it from this book. Again, I think it's a question of guessing. Of course, using the subtitle of Hans' famous book on Einstein's work. And if you haven't read it, this is absolutely essential reading for everybody. Written at the popular level, but very rightly, he talks about Einstein's legacy being rather outrageous. And here, I'm going to talk, I mean, of course, there are a lot of things to talk about Einstein, and I'm going to talk here about two aspects of it. And this I include in my title. I wanted to talk about something that Einstein's work predicted, and he was able to see about it in his lifetime, though not in its full glory. And then something that his work predicted, and he absolutely did not believe going to work. People did not see it. That's gravitational waves. And of course, we'll talk about various other things related to it in the process. So just to, as I said, it's going to be a very general talk. And bear with me if you know about all this. How many people read about gravity in schools? And the gravity that we taught in schools, the gravitation that we taught in schools, is a force. That's what people learn about. And that's what most people stay with unless they've gone to university and studied about gravitation in glory. Looking at what we now think of gravity as. Most people, gravitation is a force which is like something that pulls along a straight line connecting two things, like an invisible string. It works very well in most cases, but it causes things to accelerate, and we learn about Newton's laws. Of course, one of Einstein's enduring legacies was that it changed the way we look. What we did was, he essentially said it is not a force. It can manifest itself as one, but it is there because of a geometrical effect, space-time. In Newton's way of looking at gravity, space is empty. There is nothing there in space. Space does not have a character. Whereas in Einstein's idea, space itself has a character. Space-time is a thing. And gravity is just a geometrical effect. Space-time. It's a complete radical way of looking at it. So I thought, just to, if you are not familiar with this, just to sensitize you to where this came from. So Einstein's thing is gravity, force, and then things move in space-time along the shortest routes, geodesics, according to the curvature of space-time. That's the idea. And that looks like things are pulling each other the way Newton thought. I mean, there are very few examples in science where, in keeping the original effect, one can think of something in a completely different way. Just talk about Einstein himself. Einstein's fear of miracles, unus mirabilis, was this, in some people's lives, come together in the same year. A lot of things happened in 1905. For Newton, that was 1665, the year of the pandemic. But in the same year, he invented calculus, he discovered gravity, he wrote down the binomial theorem. All that happened in the same year. For Einstein, all these things happened in the same year. He came up with a paper of photoelectric effect. He was not working at the university at that time. Part-time registered as a PhD student at a university. And he wrote this paper on the photoelectric effect, which later was the basis of his Nobel Prize. Same year, he submitted his PhD thesis finally after a long struggle. And then he published his first paper on Brownian motion, string of papers. We don't even think of Einstein, the person who wrote down Brownian motion. And then on the 30th of June, he published this paper, which we know as special relativity. It was called something else, which completely changed this idea of space and time. Then he wrote another paper. All this happened in a single year. If you can think of doing at least one of these 6 things in 1 year, you're done for life. Why is Einstein a very curious character? And that is because he thought out of the box his entire life. There are quite a lot of myths about Einstein that people think about. People think that he was not good at school. He got the highest marks in school. Absolutely wrong. He had a couple of nervous breakdowns. His father and mother moved away to live in Italy when he was very, very young. And he was left with his uncle, who was a physics teacher. And his uncle taught him up and taught him physics. at home. And he had quite a lot of mental health issues. And he dropped out of school because of mental health issues several times. But he was always very good at studies in general, in mathematics, of course. So when he was 15, Einstein wrote an essay for Uncle Caesar. On his birthday, he was 15, Einstein was 15. Now, I don't know how many of you have ever given your uncle a birthday present, which is a physics essay. I haven't. This was an essay in physics in which he argues. It's a fantastic essay, and it's in the public domain. You can read it. This is German, but there's the English translation. There are also very nice articles in the Smithsonian Magazine on solar phenomena. And he's in that essay, he's thinking at age 15, what will happen if I travel at the speed of light in the mirror? Can I see myself in it? And he's worried, right? Because the light has to go and reflect itself and come back. And if you're traveling at the speed of light, does the light come back? And in order to do this, just shows the way he thought about these effects he knew that when you're traveling near the speed of light, things become difficult, things become counterintuitive. And he's thinking about this at age 15, long before he published his paper on the Untitled. This led to his worrying about the speed of light. And as you can see in his special theory of relativity, one of the main postulates that he writes down is that everything later on is based on that postulate. And he writes down that the speed of light is going to be the same for all observers. Doesn't matter what the speed of the source is. You have Newton and Galileo's way of looking at it. You are running like a cricket, you're a bowler. You run with a speed and you deliver a ball. The net speed of the ball is the sum of the two, the speed of the sum of the two. And Einstein essentially said, no, speed of light is such that irrespective of, even if the source of light is moving, the actual speed is the same. And what will happen is that space and time change itself to accommodate this basic fact. The basic fact is not division of velocities, but the basic fact is that space and time are going to change itself. This partially goes back to that issue I talked about. The mirror, and you're running at the speed of light. You can see how he was thinking about this when he was an early teenager. And this all came together during this time. Remember, Einstein is still outside the university system, even though he's finished his PhD. He's thinking about it. And this is why I call this outrageous legacy, because outrageous consequences of this outrageous theory gives us some really counterintuitive things. And I'll talk quickly about two of these. So as I said, we are back at what I said. Einstein's thinking about gravity being a space-time effect. So what does that mean? It means that if you have the sun, for example, and near it, the space-time itself is curved. And then as the Earth goes around the sun, it means that it's trapped inside this curved space-time and going around because it cannot escape from that curved space-time. It has to go around the allowed paths that it will go around. It's not because an invisible string is pulling it towards the sun. Completely different way of looking at it. The effect is the same. That's the idea. Now, once you start looking at it in this way, then it has other consequences. Newton's space and time were separate. Newton's space is empty. Light traveling, light is a massless particle in terms of Newton. And so gravity could not have any effect on light. In this particular effect, you can see as space-time is curved, as light travels around space-time, curved space-time will bend the contour of space. Similarly, since space has a character, we'll do other things, and we'll talk about in a minute. So Einstein's idea of gravity, I borrowed it from somebody else's explanation of it. It's a very nice graphic, where the idea is that you have mass that bends space-time, and so light going from one end to the other will actually follow that bent space-time, and so it will curve. And so you have a star there and you have a telescope here, then light will follow that contour and you're going to see the star somewhere else. Very simple prediction. Newton's theory did not have this prediction. Because in Newton's theory, light cannot be affected by gravity. As soon as you do this, this can be testable. Now, Einstein didn't realize how fast his test will come, because Einstein published the special relativity in 1905, 1915. He published his general relativity, we generalized it, brought in gravity and the curvature of space-time, all that. That was published in German during the war, where the English-speaking world was fighting the Germans. So actually, Einstein's paper did not come out of Germany to the English-speaking world very easily. In fact, it came to India before it went to England and America. You know, Meghnad Shah and Justin Bush did the first English translation of this paper, generally, and things like that. So once the war was over, and people got half of it, and essentially Eddington got a very early copy of the paper. Eddington started thinking in Cambridge. And even though it's one of these amazing examples, Eddington realized that he could actually become an observational astronomer for a month and do an experiment. And as you know, the experiment was to see whether the light bends around the sun. The idea is that if you have stars here, and they're coming, the light is coming to you, and the sun is in the foreground, then light should bend around the sun, and you should see this in two different directions. Now, how can you see the stars in the sky when the sun is there? It was during an eclipse. So he had to wait till the sun was covered. That is what you predict, but you can only see it when the sun is covered. So the next eclipse, total eclipse, was in 1919. Eddington went all the way to the west coast of Africa. With a telescope, actually, he took von Kluber, who was at Cambridge, the observational astronomer. Eddington didn't know anything about telescopes, and actually made this measurement. And in 1919, that measurement was made, and it was found that these stars, of course, it was not found on that day. 6 months later, when the sun was not in front of those stars, he had to take another picture of the same stars and compare the two. I've actually myself you can see the image of this following this, just like I said, there, but you can also see it there. You can also see it in all kinds of things. Actually, in fact, if the lens is completely aligned with the source galaxy, then what you should see, if it's completely aligned, what you should see is a ring, because there is no preferred axis, right? If they're completely aligned, the light is coming like that, 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 and you should see a ring. That was Epstein's prediction. And if they're slightly off axis, then this ring would break up into multiple images around that ring. That's what the system. Of course, the lens itself can be very complex. So the images will also be complex. Now Einstein rings are very nicely depicted. It is now modern images with Hubble Space Telescope, with ATCA, with even ALMA. You have lots and lots of images where you can see lovely. This is a single galaxy in the Mercury. You can see it in the blue. The blue is X-ray gas that's from the cluster of galaxies that's in the foreground. In one of these cases, it's the hot gas from a galaxy that's in the foreground. You can see these nice. And you can also see the multiple images of the same galaxy. This is one of the first ones that was found for the Einstein cross, in which they're not perfectly aligned, and so the Einstein ring has broken up into multiple images. So this is fun stuff. And then look at all these lovely Einstein rings that are coming out of various HST. Absolutely stunning. And just imagine that that is one galaxy, but that's in the foreground, and you're looking at it like that. Lovely stuff. Now, generalizing this, if the lens is extremely complicated, then you have complicated images. Like these clusters of galaxies. You look at hundreds of galaxies that are distorted, many of them multiple images, all are following various things. And the amount of information that's in there is just amazing. You're talking of mapping dark matter, simple, direct Fermat's principle ray tracing, no other models needed, right? There are no other assumptions needed. This is direct geometrical stuff. And these are, each of these systems are several PhD pieces work. And that's being done. Me with other people. And you can see lovely like this. Now, nice pictures. What did lensing do for us? Let's quickly talk about this and I'll go on to the next stage. One of the things is, I'll highlight three important things that lensing has already done for us. Except, in addition to giving us these lovely nice pictures, which are absolutely stunning. And it's one of these things that you can capture the imagination of anybody by showing them these things. I mean, this is just incredible, mind-boggling. So now, here, Arun Saini, when he was my PhD student, and I, part of his PhD thesis, wrote a paper long, long ago, predicting that this would be the best way to find supernovae for dark energy in the farthest universe. That paper only has 7 citations. How many lens supernovae have been discovered? People just don't cite your papers. This is an example. People forget. I mean, particularly if it's written in India, who cares? In fact, the referee of the paper discovered one of these and did not cite it. It was 2744. Just look at this. This is one of the farthest supernovae known. And you remember, the I1A supernovae actually give you the dark energy. Very, very important. 1.3457. You can see that. And it is, that's the supernova. It's in a lens system, and the gravitational lens, actually the magnification factor in this case is 2.5. In our paper, we showed that in many cases, able 20 to 18 in one of these famous clusters, you can go up to a magnification of 30. The idea is originally, you won't be able to see the supernovae so far away, even at its peak, unless it's in a lens system. This is an example. So now I think in principle, you can go to it to 2, 2.5, and imagine what impact that will have in mapping dark energy, mapping the acceleration of the universe. You can see how beautiful these things are. You catch that, and then you measure its peak, and that tells you the distance to that galaxy. So that's one simple use. Now, 100 years after Einstein, we're talking about relevance. This couldn't have happened without Einstein's theory. A new way to measure distance is another example from my work a long time ago. I had a student who did his thesis on using machine learning to find time delays between multiple images. So this is what happens. So look at this. These are 2 images of the same source, a quasar. This galaxy is here in the foreground, and in the background you have 2 sources. And you're getting to now. They're coming to you 2 different paths. So those path differences is slight path difference. So no quasar or no supermassive black hole essentially leads to a source that is completely uniform. There will be time variation. In this particular case, this is this I think is radio. But there are optical the monitoring of the quasars. And so what will happen, this is actually the first double system to be found. And once one varies, you wait a little long, and the other one will also vary exactly the same way. And you can see the variation. These are plots as a function of time. This varies, and 420 days later, the other one varies. And that tells you exactly the path difference between the two. That gives you a distance. Here's the Hubble constant, the distance inside. Now, this has been done for about 20 or so multiple systems. And this, in principle, in the LSST era, is going to be a massive industry. Massive industry. Why do you need machine learning to actually find these? You can see that instead of all these wiggles, just to find the exact time delay is a statistical exercise. Because there are errors, there are missing parts, every night, stuff like that. We have various things to separate. And finally, of course, this was all at the beginning, has been the greatest tool to expose dark matter. We know the universe is dark matter, and then the dark matter fills clusters of galaxies, and measuring how much dark matter there is in cluster scales. You just model one of these. You measure the redshift of the source galaxy, you measure the redshift of the cluster, then you model the shape of the lens, and then you find out. Okay. You mean the lens itself attenuates? Very little, because the lens itself, if you're looking at distances corresponding to ratios of 3, 4, etc. And it's true. I mean, yeah. So, but what gravitational lensing does is actually preserve surface brightness. Right? So this is the cause of the magnetic. You actually stretch it, but you preserve surface brightness. The other great thing about gravitational lensing is it's achromatic. So it's color independent. So it's not very convenient to one filter you can use another. So I'll just move on very briefly. I have very little time left. I hope I have 15 minutes or so. Because I wanted to talk a little bit of gravitational waves. That I don't have to say much because that's so much been in the news. But so I told you about Earth space-time and the fact that a massive object is Earth space-time. The other consequence of that would certainly be if this massive object moves through Earth space-time, it is going to have an effect on the space science. Einstein, in a year after his original GR paper, wrote another paper. Since he also calculated how much the amplitude would be for this ripple in space-time if, for example, two stars collide. In those days, he didn't know about neutron stars and black holes and things like that. So if two stars collide, he said the amplitude is going to be right calculation, the same calculation we do now with more compact objects. And he predicted that the amplitude is so small, there's no way any human can ever detect it because he found it to be smaller than the nucleus of an atom. Okay, so that's what black holes, I'm just going to skip these. And you can essentially look at black holes as a consequence of another outrageous consequence of Einstein, the fact that you can bend space-time so much that it will become a place where from which light cannot escape. We can speed up and then look at what happened in gravitational waves, which was discovered as collision of black holes. As you know, for the authors in the original discovery paper of gravitational waves in 2015, announced in 2016, were from India. And if you look at the reference list, we'll find that within the first 5 references, the announcement, the 2 papers from India, one, Vishweshwara, who was the first person who did an empirical calculation and showed what the gravitational wave profile will be from colliding black holes. As you know, Vishweshwar actually for a short while worked at IIA. So he mostly worked at the RRI, but later on he IIA and then also worked at IIA. And the other paper was by Sanjeev Dhurandhar and Satya Prakash, who essentially showed how to get the gravitational wave signal mathematically out of the detected. Anyway, so gravitational waves were first, even though Einstein didn't believe that it will be ever detected, was detected exactly 100 years after the publication of his general relativity. You know this that essentially what happens is that if you have two compact objects like neutron stars and black holes merging, then the space-time itself will vibrate, and you're measuring the. It comes from the fact that the reason it's so weak is that the coupling between the two sides in Einstein's relativity, and this is order for people who know is that this constant K is very weak, and it's so weak that the vibration itself is going to be very weak. We work out that for two neutron stars merging, which was ought to be the first thing that people would find, actually could be found by two black holes merging. The strain on space-time, strain meaning the change in length of distance between two objects in space-time as a ratio of that change divided by the actual length. There's the L over L with the strain, as you know. Generally 10 to the minus 21. So for a spectrometer that is a few kilometers long, that is still 10 to the minus 18 in meters, and then you can see that's much smaller than the size of. So that's the idea. So for people who don't play with numbers all the time, a lot of people here do, LIGO sensitivity is down by a factor of 3 from the size of the room. And the way it is measured now is the fact that you have an interferometer. A lot of people who do physics work with basic interferometers, like a interferometer, for example, and the fact that you have two beams of light going perpendicularly and being reflected off mirrors and coming and interfering with each other produce a pattern. Gravitational waves travel such that there's a compression on one axis and expansion on the perpendicular axis. That's how it goes. And so this particular system will be compressed on one axis and extended on one, and there will be a difference in the propagation and the effect of the propagation of gravitational waves. And that's what's going to be detected, and that's what was detected as an amplified effect. Now, I just want to give you, let's see if this works in this format. You probably know that this animation has yeah, so that's the idea. So in an interferometer, many of you would have seen this, as the gravitational wave passes, two perpendicular axes are going to behave differently. As a result, the two beams reflected from the mirrors, which have an interference pattern here, that doesn't, that's in balance, will go out to balance and you detect. Actually, this is very simple. In the LIGO detectors, these are 4 kilometers long, and even it's not 4 kilometers long because there's a cavity, a fabricated cavity in each arm where there are 100. Each beam goes back and forth, so actually there are 400 times things like that. So there are various ways of magnifying the effect to make it such that it comes within a measurable range. So this was the original LIGO at Hanford. There are 2 in the US that discovered first the effects of the merger of 2 black holes. And this is most famous plot from the 2015 to September 14th to February 16th in 2016 when it was announced. They had to keep this news undercover for a very long time because people were trying to figure out whether this was actually a detection. LIGO detectors are sensitive enough that it can detect any wave striking the coast of the country. In fact, one of the things that we were worried about was whether LIGO on that day, at that particular time, had detected a thunderstorm in LIGO. Just to put you in perspective, that's the kind of sensitivity. So everything it detects is noise, but amongst the million forms of noise, there is that gravitational wave signal which you can detect because people like Vishu simulated these things and gave you the waveform. The people like Dhurandhar and Satya Prakash told you, if you know what the waveform is, then you can find that needle in the haystack. With the knowledge of the waveform, matched with the techniques that you can match the pattern in the noise and then find something that's many orders of magnitude lower than noise level. So that's the idea. And so this is what, so these are the two places at which the detection happened. And I just wanted to show this picture because what happened was when this was announced, after a lot of secrecy, we organized at the IIA auditorium. We called a lot of reporters. We couldn't tell them what it was. The announcement was 10 a.m. Washington time, which meant 9 a.m. Washington time, which was 10:30 p.m. in India, calling reporters of major newspapers and TV stations to come and attend the press conference at 10:30 p.m. without telling them what we are telling them. It's a challenge, and we did that. And in fact, as you can see, right in the front row, we have Professor Nalika and Professor Dadich, and in the middle was Vishweshwar. And Vishweshwar, at that time, of course, retired. He passed away a few months after this. Then he was in Bangalore. And I called him and I said, please come. I'm going to show you something that you hadn't dreamed of. 1970 Nature paper, he actually published that waveform. This waveform is in his 1970 Nature paper. Right? And he used 1970 computers, card computers, punch computers, to do that simulation. And he wouldn't come. So I said, I'll give you, we worked on him, and his wife came. He was there in the audience. I could see the tears in his eyes, what he had done in 1970. Somebody has detected it. So yeah, so all this, Amul also. So this is, I love this one. I love this one, Amul of course does everything. But Viban produced this amazing picture showing the short-chain radius of each of these black holes that were discovered on the Indian map to show how big these things are. This, I asked him to do this because I wrote a Bengali article in Anandpur. So now the LIGO scientific collaboration has a very large number of institutions. The LIGO India science collaboration is huge. And it did this amazing discovery of 2 neutron stars merging. There are 2, if not 3 such detections already happened, but this is the only one in which, sources for which the optical counterpart has been found. And that led to an amazing campaign of in all these different wavelengths, different parts of the electromagnetic spectrum, corresponding electromagnetic follow-up. And this is going to be the thing. Only one has been done now. A lot of people at IIA were involved in it. Sudhanshu was then in South Africa. He was involved in using South African telescopes to follow this up and stuff like that. So there's a lot of people. This is the future. And in an audience full of multi-wavelength astronomers, electromagnetic astronomers, this is the exciting bit. Now, I'll end by saying that what the gravitational wave mergers are giving us from the outrageous predictions of Einstein is not just giving us gravitational waves from merging compact stars. It's now changed our knowledge of compact objects. Here's the most massive one that was found in the last run. Of course, the run was also shut down because of COVID. The last 3 run was cut short, but before that, there was a merger which led to about 145 or so, 150, I think, solar mass black hole from two black holes that are about 80 to 70 solar mass black holes. So that's something getting into a range, as you can see, of what we call intermediate mass black holes. Before this, we knew that there were solar mass black holes. Get from X-rays were about like 5, 10, 15 times the mass of the sun. You get the first LIGO detections were 30 times the mass of the sun, 40 times the mass of the sun, becoming things that are 60 times the mass of the sun. Now, the masses, just stay with this if you haven't seen this picture, stay with this for a minute. These are the masses of these objects that have been found. On the y-axis is times the mass of the sun. These are all black holes. In each LIGO event, find 3 black holes. The 2 black holes emerging to find another 3. So these are all connected in threes. And you can see how all these blue ones are LIGO detections. There are 50 of them that are still now confirmed. There are some that are unconfirmed. The ones here are electromagnetic black holes. These are all found in X-ray binaries, in binary systems from X-rays, Chandra and other XT and stuff like that. Neutron stars that are found in X-ray observations and also through pulsars. And then LIGO Virgo has also detected a few neutron stars, because there are not only neutron star collisions that make higher objects like black holes. There's been at least one case, if not more, of a neutron star and a black hole merger from the black. So these are all in here. Just look at this map, and this is all in the last 5 years. Einstein would never have wanted to come back. I mean, just look at what came out of seemingly innocent prediction he made about gravity. So this is where I want to just stop, and just to tell you that now, of course, we are going to do LIGO India. All these places were found for the third LIGO detector. Huge amount of work went in identifying the place, finally went there. And now, 4 labs that are actually working on building will be here in Hingoli, are around us, responsible for the optics, IIA, science, a lovely picture of the same things it will look like. Looks pretty barren now. Lots of important things will happen there. I don't want to go there. Most important part of it is what we are doing now, the outreach. The area is very, very important for somewhere in the middle of nowhere in central Maharashtra. High-tech observatory, the only one of its kind that there is in India, this kind of scale will be sent. So we have to talk to the people out there. So I have teams out there, schools who are working not only the Hingoli district, but in Parvani, the neighboring district, and we have some plans for that. We are working in the schools, so it's very important. Social media, please look us up. And I just want to leave you with the best books I can.
Thank you, Professor Rai Chaudhary, for this amazing story about gravitation and sharing us so much of information that, at least, I was not aware of. So I would now invite Professor Pandey to carry out the daunting task of Q&A, because let me remind you that this lecture is in hybrid mode. So we will have questions from not only the audience here, but also on WebEx as well as on YouTube Live.
Is somebody monitoring the online stuff?
Yeah, so we'll take questions now. So, Firoza, please.
Non-operational value. Second on the choice of decision. Let's go to the first question. For reference, I will point out that Supernova 87 it goes by audio. Not only said if it is true, because the recording tape had more than those came in. And a graduate student came in on the weekend, noticed that the recording tape and went and changed it. Now, obviously, during the time of pandemic, one doesn't really expect that graduate students will come to me now. But has there been absolutely no setup to record the
Very interesting. So actually, there are three sets of detectors running now. I did not mention Virgo, I should have. Did not mention Virgo, which is now near Pisa, which actually started observing in the third run jointly with LIGO. And I should say that many of those three measurements were done by LIGO and Virgo together. Then there's Gagra, which is a 3 kilometer in the Kamiyaka mines. Kilometer, it's observing just before the pandemic. And they haven't detected anything yet. Now, the thing is to keep the observatory running, there is a huge amount of work that needs to be done. You can't just leave it and go away. Because the vacuum, not at all vacuum, right? And you have the cavities, which are very repairable. They go out of tune sometimes. And typically you have maybe 4 or 5 hours before some cleaning needs to be done. And so the 24-hour crew, mostly of graduate students and postdocs, they have a LIGO Fellows program. We send people from here. Like we have some of our IIA students who've actually been there on 24-hour duty in the tunnels. And you have to, there is a recipe of things that you can do, etc. But in fact, one of our students wrote a LIGO, like a Siri program, in which suddenly things go out of tune. What is the first thing I should check? So all this, so you could not actually absolutely run because both the places. Louisiana is a really backward place in terms of education. Washington State, both of them. Washington was the first state that was hit very badly. So during now, there was a shift. Just because of this, you cannot run LIGO for more than 6-8 months. Each run is about a year or 3 months. It was coming close to the scheduled end of O3. There were 3 months left, and they have to shut down. And for 2 years, nothing has happened. Now O4 will start in December. And during this time, it was scheduled that a lot of changes will be made. Actually, a lot of upgrades are being made. Laser is going to street lights and all kinds of things are going to happen. These changes have been made there in the city. Not that people have wasted their time. And our deal was that we're going to send the Indians there to see what's happening because the tunnels are not open when it's vacuum. But that we could not do. But we set up a video link. There were body cameras like police use, which people wore going into the tunnels, doing little things, and there were people here in Arakat, in Ayuka, watching them. So some things have happened. So that's the short answer to because there's also a longer answer. And I remember your second question. Let me just address the second question.
Yeah, bravo.
The second question, I'll come to you in a minute. Second question was about
the choice of
site. The choice of sites is a very interesting question, and that is also a very long story. Tarun Sarojan has written a wonderful article in LIGO magazine on it. If you Google it, find it. The challenge was to find a place that has very low seismic noise and is at least 20 kilometers from a railway line. Very hard to find. And less than 10 kilometers, not 10 kilometers away from the nearest district town. You need an airport within 200 kilometers. These are all these constraints. So I said Kolkata. Rajesh and his undergraduate students wrote Python scripts to look at Google Maps. Google Maps were not good enough for the terrain. So ISRO gave us the Cartosat maps. Cartosat maps of the entire India. These little code went and looked at how flat part will be. We're going to have a 4-kilometer long flat, pipeline, right? Stuff like that. So finally, the place in Rajasthan that was shortlisted, and this place. And there was one in Madhya Pradesh. Then somebody had the brainwave look through the projection of Indian railways in the next 25 years. We found that the Madhya Pradesh site will have a railway line taking marble from Kota to Bhopal. So, no. So this is only part of the story. Please read that story. Tarun has written some of that.
One comment. Okay.
Yes, good point. And I've asked this question a lot. It turns out that the Deccan Plateau is the quietest seismically quietest place in the whole world. Deccan Plateau is fantastic. In fact, this would be chosen if you look at the vibrations, normal ambient vibrations between 0.1 to 100. It's 10 times quieter than anywhere in the US. So we can build a better instrument here than anywhere. Except for Latur, that earthquakes like that are spikes that happen. It has nothing to do with the regular seismicity. And that will happen. And if something like that happens, it stop the senses, sensing the earthquakes, etc. So it doesn't matter. Other than that, due to popular belief, that area is the seismically quietest. Yeah, that has been done. That has been done. In fact, one of our major advisors was the deputy director of GSI, who specializes in that region, with huge amount of data because Nanded University has a very active geology department which has been studying this. A lot of data is. Very, very interesting question. Now, this is, of course, the subject of a lot of people that I work on this. And the idea is that, just like the X-ray background, the cosmic background, the gravitational waves from a very large number of natural sources that are happening. There is supernovae happening. So that certainly leads to gravitational waves. The stars colliding, there are all kinds of things happening. Normal astronomical processes in ways, but they are singly not powerful enough. So, we want to look at them statistically in a combined manner. But it turns out that signal, these LIGO detectors have sensitive around the 1 hertz, 200 hertz, that kind of thing. There, the stochastic gravitational wave background way, way below the noise level. The stochastic background is high in the much higher frequency. Hertz, so there, people were depending on things like ESA. It probably fly in 2040, I don't know, 2025, and other things. So people are already planning. In fact, there is a proposal. Satellites. These things are better done in space rather than state of the. There's some still it will remain in the heart switching, right? Not in the stochastic. No, actually, there is some exercise that is going on in stacking the various gravitational wave detections to see whether there are noise can be brought down in some stochastic. So people are already doing that. 50 sources is very difficult. Just wait till we come to 5,000. Slowly we will.
You have another one?
Thank you. Let's take
Yeah, so let me ask, I come back. So on WebEx, if any of the online participants want to ask any question, I would request them to unmute and ask your question. How to unmute when the host or raise your hands. You can either raise your hand or put it in the chat box, please. Okay, so in the meantime, I think Vagish has a question. Vagish?
Yeah, so I was wondering that
very, very good question. Extremely good. See, the Michelson ball experiment had a very important test. That medium, what is the medium? And later talks about light going in very free space, etc. But in the conventional sense, anyway, and that medium was supposed to be ether. And then the idea is that as the spinning is going this direction, and then so if there's ether, which is a medium, it fills vacuum, then it will have a current in that direction. And so if you have the Michelson mole experiment, which is the Michelson interferometer in this direction, that ether will have a different speed from this direction, and light speed will be different. That's what we expected. And that was a null experiment. Did not detect a difference between the speed of light along the two arms. That helps Einstein. This is only 5 years later. So essentially, I mean, Einstein says, this is why we didn't find a detection, because it does not depend on a medium. And in fact, it doesn't require a medium.
So, Firoza, you want to please use the mic.
What would be the furthest distance? It's constant.
Good point. I don't have these numbers on the top of my head, but I'll give you round numbers. Actually, the black hole merger now, the pre-detection, the black hole merger distance was supposed to be smaller than the neutron star merger distance. Now they are going up to about 300 to 400 megaparsecs. That's expected. And black hole and neutron star is saying, supernova, I don't know. Probably much less. So if it's supernova explosion. Yes. That I don't know the answer to that. And I find a very interesting question, but I don't think it's going to be.
I would imagine that it could be very good. Megaparsec.
Oh, yes. Then your question goes back to the 87 acres. Would you have detected 87? I don't know. I mean, I've seen calculations that show that 87 would have been detected by our gradient over sensitivity, right? And so if it's that close, you're not going to verify it. This is only 50 kiloparsecs.
We are overdue for a galactic.
Oh, yeah. That's another, very good concept. Yeah, because it's behind the galactic plane, you can't see it.
You can't see it.
Should be able to see it. I'll give you the answer. This is not, I don't know what the actual equation is for.
Any more questions from the audience here? Anybody else on, Abhagis shares another question.
Yes, maybe elaborate and I could add still contribution to this statement, right? And it must be matter property are there. In what?
But then you can actually, what you do is, what you get from Maxwell's equations is that light is a wave. You have to make it waves. As soon as you say waves, then people started talking about medium. And I'm not personally sure whether Maxwell believed in a medium or not. But Maxwell's waves could propagate in free space, right? Does anybody know there would be people here? Do you know whether Maxwell actually believed in the? I'm not sure, but I don't think he did. Because his equations, looking at them now, clearly show that an electromagnetic disturbance can propagate in free space. That's what Einstein is doing, Actually, the Maxwell bond experiment is quite an interesting experiment because as an experiment, it's fantastic with the Nobel Prize, etc. But it gave us much more than it intended. It gave us light.
Yeah, so any more questions, Jayant, on the okay, so if there are no more questions,
Then we would go for a group photograph in the east lawn, and then we will proceed for high tea in the west lawn. So Yogesh will take over. Not required, yeah. We are outside. Sorry, yeah. Please, we forgot one. So this is Sabina.